and I'm really happy to be here. I'm sorry I missed the first 2 days of the workshop. And so today I'm going to talk about self-gravity and gravitational instability in mostly in protostellar disks, and what we did and we are doing with phantom with these systems. Okay, so first thing I would like to point out is that self-gravity is very important in every astrophysical scale. So we really need to take into account self-gravity in astrophysics, and so we really need a code that is able to deal with self-gravity. And in this self-gravity is very important, for example, for the structure of planets, like for Jupiter, so scales to 10 to the 4 kilometers. Then it's very important, for example, in Saturn rings, because they are very thin, very cold structures, so the effects of self-gravity are very important. Then they determine the structure and evolution of stars. And there is a bit of echo. Francois?
Yeah, that's me.
Could you mute? Thanks. Okay. Then can be important in protoplanetary disks. This is what I'm going to focus on today. Then for the formation of stars, protostars, and protoplanetary disks, it's important to consider self-gravity in molecular cloud cores. Then galaxies and large-scale structure in the universe are also determined by self-gravity. And a possible outcome of self-gravity is gravitational instability. So gravitational instability is just a linear electrodynamical instability, which can arise in self-gravitating systems. And here I'm showing you examples of different cases where gravitational instability is actually important. So it can be important in the process of star formation. It's known as Jeans instability in that case, but the physics is the same. It's very important also in protoplanetary disks, and for example, this is a gravitationally unstable disk which is fragmenting in gas, but it can also fragment in dust, forming planetesimals. So like in this study, what I really like about this is that it seems that gravitational instability is able to create things in astrophysics, from stars to planets. And so what do we need to know about gravitational instability in disks in this case? So this is the main equation we need to know. So this is the dispersion relation for a gravitationally unstable disk. And here, basically, we have all the ingredients we need to understand this phenomenon. So we have the competition of stabilizing and destabilizing effects. So the stabilizing effects are here the sound speed, so the pressure support, and the rotation of the disk, which is here with the epicyclic frequency. And the destabilizing terms when we consider gravitational instability is the surface density, meaning the mass of the object. And it's possible to determine whether a system is gravitationally stable or not by evaluating this dimensionless parameter, the numerical parameter, and the Q equal 1 is the threshold of instability. And it is very nice because it basically is measuring the stabilizing effects over the destabilizing one. And this same equation actually works very well for galaxies and protoplanetary disks, and I will go back to this comparison later in my talk. So how can we trigger gravitational instability? Because of course, in order to have gravitational instability in a disk, the disk must be either cold or massive. So there are ways in which we can trigger this phenomenon. So let's start with a gravitationally stable disk, so with the numerical parameter higher than 1. And the first path to trigger gravitational instability is through cooling. So we can cool the disk, so the temperature of the disk is decreasing. We can assume radiative cooling, we can impose a cooling prescription, but the idea is that the temperature is decreasing. At some point, Q reaches the threshold equal 1, spiral structure develops, and the spirals are shocking the material, and so they are increasing the temperature. So if there is a balance between the cooling and the heating provided by the spiral, we have a self-regulated state. We observe that this is possible, and this is the first way to trigger gravitational instability. A second way, which is actually what I'm mostly interested in this talk, is to trigger gravitational instability by adding mass rather than by modifying the temperature. So the idea is that we have a disk which is receiving mass from the environment with a mass injection rate. And at some point, the mass of the disk is high enough to trigger gravitational instability, so Q equal 1. And what happens in that case is that the spiral structure is transporting the mass, part of the mass that is injected is then accreted by the central star, and we can reach like a balance between the accreted mass and the mass we are injecting. And this is the equivalent of the self-regulated regime I was talking about before. And it is possible to show with simple analytical considerations that these are the stellar accretion rate and the disk accretion rate. So how the star and the disk mass changes as a function of time in the self-regulated state, where here this is the injection rate from the environment, and the Q is the disk to star mass ratio. I will explain this a bit better later. So let's speak a little bit about cooling and what we did in the past. So this is a phantom simulation of a cooling-driven GI disk. You see that there is the spiral structure, and the idea is that the cooling is really useful and we're really handy when we want to perform numerical simulations, because it's really easy to implement in a code. And what we have been mostly doing so far is to use a simple beta cooling prescription. So the idea is that we have the cooling time scale, which is proportional to the dynamical scale of the disk. The factor of proportionality is this beta, and this is not a realistic prescription at all. But it's very useful to understand what are the general scalings for these disks. And the idea is that when the self-regulated state is reached, the spiral arms can transport angular momentum, and we can describe this transport with an alpha viscosity, and alpha is inversely proportional to beta. And the morphology of the spiral is determined by the disk to star mass ratio. So the more massive the disk is, the lower the number of spiral arms the disk will have. And finally, what is also important is to understand what is the pattern speed of the spiral. So as you can see from this video, I will show you again. So it's not really easy to define a single spiral structure, a long-lasting spiral structure in this case. The idea is that we create spirals and they shock and they are quickly destroyed and recreated again. So defining a pattern speed is not very easy, but what we can do is to measure instantaneously what is the pattern speed, and it turns out to be proportional to the angular velocity of the disk. Of course, this is just an instantaneous pattern speed, because if it was lasting long, what will happen is that the spiral will just wind up and disappear. So this is just an instantaneous one. So the spiral will travel a bit and then will dissipate and recreate again. We used cooling and GI a lot in previous works, for example, to study kinematics, kinematic signatures of gravitational instability in protostellar disks. For example, this is a work by Cassandra Hall, where she introduced this concept of GI wiggles, which are kinematic perturbation due to the presence of a GI spiral structure. And we also use this model, for example, in a paper by Jess Speedy, modeling the disk around the star Auriga. And also, GI and cooling was very useful when we studied planet formation in this system. And in particular, when we studied the interplay between dust dynamics and gravitational instability. So in these works by Sal and myself, I think we showed that if we have Stokes particles, dust particles with Stokes number between 0.1 and 1, dust collapse is possible inside this structure. This was already been observed 11 years ago by Ken Rice. And actually, a couple of weeks ago, Ken Rice published another paper where he basically confirmed the same behavior, but with a sharing box simulation. So yeah, I think that we are pretty confident to say that gravitational instability can create Earth mass planets thanks to the dust collapse. The problem is that we need to have particles with these sizes in a very young stage of protostellar disk evolution when the disk is unstable. And so the question is, can dust particle grow up to this size fast enough? So when we want to understand this, we need to compute a quantity that is we need to understand what is the typical collision velocity between dust grains. And we are trying to do that, but we are really limited by resolution. So we really need high resolution in order to resolve a collision between two dust particles, because a collision is resolved when the distance between two particles is smaller than the typical. Of course, as you can imagine, when we have a Stokes number of 0.1 or smaller, to resolve. For example, here we have phantom simulations with gas and dust with different Stokes number. You see that for example, Stokes equal 1, we can resolve 20% of the collision, while, for example, for Stokes 0.1, just the 5%. And it's really difficult to say something quantitative when we are resolving a small number of particles. So what is the solution? The solution can be Shamrock, and this is a reminder for Timothée to implement self-gravity in phantom, and also dust, of course, because we also need dust. Otherwise, we have Kat Lydon. She's a PhD student in Cambridge. She is about to be in the job market, and she's working this problem, but with a sharing box simulation. She told me to say that she's open to use SPH, so just to tell you, so if you're looking for a postdoc, she may be the one. And so GI and cooling, we used it a lot, but is it really realistic? So it's not realistic, at least the beta cooling. And also what Sal showed last year is that when we couple hydrodynamics with radiative transfer for gravitationally unstable disks, the idea is that the stellar irradiation is too strong for gravitational instability to kicks in. And so basically the cooling is not, let's say, a viable way, at least in this parameter space, to trigger gravitational instability. And a similar result was also shown by Kat in her recent paper with shearing box simulations. So she basically studied what happens when gravitational instability, to gravitational unstable disks when they are irradiated. And she basically shows that for high level of irradiation, the transport of angular momentum goes to zero, meaning that gravitational instability is not able to transport angular momentum in this case. Okay, so now GI and info. So the idea is that now we want to understand a bit better how gravitational instability works when we are adding material rather than modifying the temperature. We have observational evidence that this is happening in the planetary disk. For example, this is the disk around the Biorige in a paper by Jess Speedy this year, where she showed that it's possible to trace streamers from the cloud up to the disk. And actually what you can see is that there is a shock in the merging zone between the streamer and the disk. So disks are interacting with the environment. And under a numerical perspective, the study of gravitational instability triggered by infall has been tackled by, for example, Caitlin Crater in a paper in 2010, but with, let's say, a complex setup. The idea is that she simulated the collapse of an isothermal cloud mediated by a disk. What we wanted to do here was something simpler to really understand what happens and if a self-regulated state can be reached or not. So the first step we did was to write a 1D evolution code in which we are adding a source term. So this is the typical diffusion equation for the surface density of protoplanetary disk. Here, this is a source term, basically indicating that we are adding mass at a given radius with a fixed injection rate. So this is very, very simple. So this is basically a delta function at a given radius in the disk. We used a viscosity prescription for the kinematic viscosity that mimics gravitational instability, meaning that it activates only when the Tumri parameter is of the order of 1, so when the disk is unstable. And of course, here an hypothesis is that the disk is locally isothermal, and this will be an hypothesis for all my talks. So this is like the opposite compared to the cooling. So here the temperature is constant throughout the simulation. So these are profile of surface density and Tumri parameter to show that surface density increases because we are adding mass, and also the disk is spreading because the mass that is added to the disk is redistributed between the star and the disk in order to maintain this equilibrium for the self-regulation. And you can see that self-regulation actually is happening because the Tumri parameter profile is constant of the order of 1. And where I show the evolution of the global parameter, so star mass, disk mass, see that as a function of time, star linearly, so proportionally, and their ratio But then, so phantom. So this was 1D, but we of course wanted to see how this looked in 3D. And so we last year when I went to Monash, we implemented an injection routine to inject SPH particles at a given radius with Keplerian velocity. So that is the velocity at that radius, and matching the aspect ratio of the disk at that location, meaning that the disk here is locally isothermal. You can use this routine if you use the setup Dusty ISO-SG disk or just ISO-SG disk, and it's available in every version of Phantom older than June 2024. And so at this stage, the injection is really simple. So we're injecting with a fixed injection rate at a given radius. It is possible also to inject in a Gaussian ring to be pushed to the repository. I have it, but not yet public. And also works for distorted disks. I worked with this on this with Beck. And yeah, so as I told you, the disk is locally isothermal. So what would be nice, maybe I can work on this during these days, is to implement this injection for adiabatic disks. Okay, so these are the simulations. They're beautiful, I think. And so we decided to run just 3 simulations for this work, because these simulations are really, really long. So the typical time scale for self-regulation to occur is of the order of 10 to the 4, 10 to the 5 years. So it's a bit long time scale. And so here are 3 simulations with the 3 different aspect ratios, which are basically determining what is the final disk to star mass ratio of the disk for different time steps going down. And what it was very nice, because we compared the results from the 1D code, the solid lines, with the SPH simulation, and we find a wonderful agreement, meaning that this self-regulation is happening also in 3D, not just in 1D. And here I would like to show you a comparison between the infall and the cooling. And I mean, apart from the speed of the movie that is different because of, not because of the physics, just because of the movie, you see that the disks are, I mean, the morphologies have analogies and also differences. And now I'm going to explore a bit more this comparison. So first of all, what are the analogies between cooling-driven GI and infall-driven GI? The first thing is the scaling of the morphology with the disk to star mass ratio. So from the linear theory of gravitational instability, we expect that higher disk mass disks have lower number of spiral arms because low M modes are unstable at a higher disk to star mass ratio. And we see this scaling in our simulation. So basically, this is the dominant mode computed from Fourier analysis as a function of the disk to star mass ratio for different simulations at different time steps. And we see that, I mean, we recover this scaling, which we also recover in the cooling case. But then, so here I'm comparing infall and a cooling simulation with the same disk to star mass ratio. And this is the power spectrum of the spiral at a given location in the disk. And so there are analogies and differences here. First of all, since the disk to star mass ratio is the same, the dominant mode that M equal 2 is recovered in both simulations. But what is different here is that you see in the cooling-driven scenario, we have a lot of power in high M modes, while we don't have such power in the cooling case. So which basically means that for the infall simulation, we have a long-lived global spiral mode. So the spiral is cleaner compared to the cooling case, where we have a superposition of different short-lived modes. And in order to understand if this global mode is really long-lived or not, what we did was to track the spiral at different snapshots and compute the pattern speed of the spiral for the infall case. And what we see is something very different compared to the cooling case. So in blue is the angular velocity of the disk, and in green is the angular velocity of the spiral. So basically this spiral is rotating with a fixed pattern speed. So it's basically rotating as a rigid body, which I say, it can make sense because we are forcing the spiral at a given location by injecting particles at a given location in the disk. And not surprisingly, indeed, the pattern speed is exactly the rotational velocity at the injection location. So the velocity of, let's say, of the forcing terms we are adding. And but this is pretty different compared to the cooling case. And now I'm going to make a couple of comparisons with the galactic dynamic field. And so what we did here was to try to understand why, for example, in this snapshot, we couldn't really follow the spiral in this region here. So just to give you a couple of information more. So the injection radius, which in this case is 1 in code units, can be also called the co-rotation radius, because it's the radius in which the spiral is rotating at the same angular velocity of the background disk. And then these two lines here are the inner and the outer Lindblad resonances, which are important quantities in galactic dynamics, which basically determines two regions in the disk where the spiral is resonant with the fluid. And yeah, so here I'm showing in a polar plot the divergence of velocity field of this spiral, and we found that this quantity is tracing very well the spiral arms. And you see here that the spiral really breaks in this region, which is the region between the co-rotation, so the injection location, and the outer Lindblad resonance. And so it's possible to use the dispersion relation like in a dimensionless form. And and basically we can use this equation to determine what is the radial wave number of the perturbation, given this parameter. For example, the Tumri parameter and the scale height of the disk. If we solve this equation, we have these propagation diagrams. And what we see is that from co-rotation to the inner disk, we basically have that the radial wave number is a real number. So we have normal wave propagation. But in the region between co-rotation and approximately the outlet Lindblad resonance, the wave number is imaginary, meaning that here the wave is evanescent. So the idea is that we have like a quantum tunneling effect from this region to that. So the idea is that in this region, the wave cannot propagate and can then freely propagate outwards. And this is a very last thing. I've just started thinking about it, so I mean, happy to hear your suggestions. So when we look at the mass accretion rate of this, in this case, you see that there is some variability, like they seem to be like burst, and you really see them as like pulsation in the simulation. So we know that for high disk to star mass ratio disk, we can have such kind of burst, but we wanted to understand why in this case. And so this is a phenomenon really this is studied a lot in the context of galactic dynamics, which is called over-reflection at the co-rotation radius. So the idea is that at co-rotation, the sign of the group velocity of the wave changes. And so the idea is that it's possible, if a wave is hitting the co-rotation, can be transmitted outwards, but the sign of the group velocity changes. So in order to conserve the total energy, we need to reflect the wave with twice the energy inside. So this is known to happen in galaxies. And what is also known to happen in galaxies is that we can create a resonant cavity in the inner part of the disk. So the idea is that if the Tumri parameter is higher than 1 in the inner disk, then the wave can basically bounce and go back. And in order to create a resonant cavity, the bounced wave needs to be in constructive interference with the long wave here. Or constructive interference. So what because it's a bit long procedure. And I mean, what I wanted to verify is whether this condition is met as a function of time. And if this condition is met, it should, the idea is that we are accreting mass into the central star with a significant rate. So the idea is that the hydrostatic height of the disk is changing because h is inversely proportional to square root of m. So the disk is becoming thinner and thinner as a function of time. And so I evaluated this integral as a function of time Basically, this the condition is met when we have the red crosses, and the period, like it's a very rough estimate, the period seems to be consistent with the one we observed from the simulation. And in order to verify whether this is happening or not, we decomposed the spiral mode into long waves, short waves, leading waves, and trailing waves, which are different flavors of a density wave. And the idea is that if we want to have this phenomenon, in the inner part, we need to have a superposition of a short and a long wave. And what it seems is that we have a very strong short wave component, which is what we expect, with a long wave component as well. What is interesting is also we have a leading wave contamination, which I still don't understand why, but it's something to think about. And for the very last slide, what about infall and dust dynamics? So what happens if we add dust? So this is what I'm trying to do now. This is the only thing I have. So it's like a snapshot after a very short time scale. This is completely decoupled dust. And you see that the morphology is, I mean, it's very beautiful. It's a bit strange, so still need to understand what's going on. But this is one of the next steps. And with this, I leave you with my conclusions. And thank you very much for listening.
So if I remember correctly, so you inject particle for the infalls in an annulus that is within this plane, right?
Yeah, yes, yeah. So the particles I'm adding have also a Z component, which is basically the Z position is randomly drawn from a Gaussian with the scale height of the disk being the typical side.
I was wondering, so what if you vary like the injection radius? Like, do you get different pattern? And secondly, what if instead of injecting in an annulus, you just like use a low density envelope? Would that change any of the conclusion?
Yeah, so this is what I'm trying to do now, is to basically generalize a bit this injection procedure. So I tried to inject in a Gaussian way, so in not just in a single location, but more spread. What seems to happen, but I haven't looked into those simulations well, is that, I mean, we are exciting different modes because we are like exciting waves at different location in the disk. And the morphology still seems to be pretty clean compared to the cooling one, but need to look better into that. And as for the asymmetric injection, well, I have no idea, but it would be great to see. Yeah, thanks.
One more question, please.
I was wondering if you're going to, once you take this analogy with galactic analysis, it looks like the inner part around the inner limb of resonance looks a bit like a bar with more surface about.
Which makes
sense, especially in the dust. And there are all sorts of
the
dynamicists people have developed all sorts of machinery to look at this in terms of like sections and sections of this sort of thing. And you can look to see whether you have X, Y, and X2 orbits.
Yes, no, actually, this is very interesting because in galactic dynamics, like having a bar is like a natural consequence of having a high disk mass galaxy. And so, what would be actually very interesting is to perform like a proper global analysis of spiral modes as done in galactic protoplanetary disk characteristics.
Easier to measure as it's one square.
Would be great to see. Thanks for the suggestions.
All right. Well, then I guess short one.
Yes. Separating things that never receive infall, as in if you inject for a limited period of time material and then you stop, does it change the spectrum or?
So I haven't really looked into that. I mean, here what I'm mostly interested in is the gravitational instability, which is triggered by the infall. I think this question may be more related to, for example, what Josh is doing. So just injecting particles, injecting like
limited
amount of time, and also not in gravitationally unstable disks, because of course we require a bit of time for gravitational instability to occur. So this may be more related to what Josh is doing.
Okay.
Yeah. Do you have looked at if you have global modes? Like no radial node.
You mean in the pulsation?
Yes.
No, I haven't looked into it. I'm really starting to look into that now. So yeah, I mean, I have to have a look if there are global modes.
I would be very interested to know if you have global modes. Because I think there are works on those global modes on stars. I think also.
Yeah.
There are dispersion relation and so on.
Okay, I need to have a look at that. Yeah, thanks.